There are no black markers, but hopefully. Yeah. Okay, can you hear me? Let me make the sound louder. Uh, so it's the sound okay? I hope so. Let's start. So today is a really nice lecture. I mean, I wanted to do more last lecture, so we'll move to this lecture. It's also the last lecture that the theory is difficult. Afterwards, it will be much easier. So, we will speak about responsive systems. So, for example, a computer program wants to play chess to other agents. And so we will define a set of environment, for example, chess players, and the game will be chess. So we will get reward 1 if we win, maybe reward 1/2 if there is a draw, or a 0 if there is if we lose. So idea is that we have 0, 1 rewards, and given a set of environments, we want to build an agent that collects rewards optimally in each environment of the set. So this is the goal. And so we want to do this for every set of environments, but not for every set. Does there exist at least one such optimal agent? So the plan is today that we will prove that if there exists such an agent, then the one based on Solomonov idea, we will need to tweak it a little bit. So Solomonov ID will now be, the strategy will be use random programs to simulate environments, use random strategies to play against it, and then select the best environment that you found. And we will prove that this strategy works, provided there exists. So the property is self-optimizing. We prove that if self-optimizing exists, then this strategy works. So that's the goal for today. So seminar is just for questions. So I was a bit under time pressure. So I only wrote half of the lecture notes so far, and there is some technical issue in the very end when we translate the main result to Solomonov prior. So like last lecture, we will have some kind of mixture Q that we will use, and then we will need to translate it to random programs. And there, some choices need to be made, and I didn't work them out yet, but I will do it in the notes. So this will be chapter 6 and 7 of the book I shared on Telegram. So I don't know, I don't have the Hutter book. So and it looks like this result of today is unpublished, and also I seriously simplified the proof so that it becomes manageable. But I hope it will be manageable. Okay, so this lecture proof will be much easier compared to previous lecture. Unfortunately, many more definitions because we have a few more sets. Okay, so what we will have a finite set of actions, finite set of observations, and finite set of rewards. So here are finite sets. And the rewards will be real numbers in the interval 0, 1. 0 will be inside. So note that we will do like last time, bound all the rewards by 1. So Artyom, yeah, it's readable. If I'm in the back, it's readable, just readable. So finite sets. Okay, so this is easy. And so what is the game? So there is, in each round, 3 things happen. First, agent choose action. Then environment gives us some observations and also some reward. And so for the chess example, so the actions, they are all the legal moves on the chessboard. Observation is move of opponent. and the reward is always 0, except if we capture the king or if some rule for draw is triggered. So there's like 13 move rule or something. Okay, so let me, I should have printed the lecture notes. Let me have a quick check that I, so what else should I say? Let me quickly check that I don't need to, I made some plan for what I should say, but of course I forgot already. So example chess, I did. Okay, so then let's say what is policy and environment. So I will use some notation when I say prob of the set A, that's just probability vectors of the set A. And so that means, so P is in prob if and only if P maps elements of A to 0, 1 and sum in A. So I will use subscript. Well, we don't need to too much. So sum over all element A is exactly equal to 1. Okay. So and now we can say what is a policy. We will use probabilistic strategies. So well, first of all, I need to say what is the information that we have. So note in each round we have action, observation, reward. So the history of a game will be triples, a list of triples. So the history will be action times observation times reward, and this finitely many. So these are the list of histories. Policy will give us a history, finite history, and tell us an action, but not deterministically. It will do probabilistically. So it will go to probability on the actions. So this is very natural definition. We give history and we get probabilities. Environment, and so in the book uses always the letter nu for environment. It will give us a history and the last action, and it will give us probabilities over observations and rewards. Okay, and now we can define a measure over histories like we did before. So a measure is a mapping of strings to numbers that sum up to 1. So there is conditional measure. And so I don't like the notation in the book. They use nu superscript pi. I will just multiply them because that's what you do with conditional probabilities. So let's say that pi nu is semi-measure. And so pi nu just maps a history to numbers of 0, 1, and it's defined by induction by q nu of empty equal to 1, and then we have q nu of finite history. So okay, let's call it. So I will use h tilde because h later will be used for action n for infinite sequences. Action n, observation n, and reward n is equal to pi nu of history star. And so now the logical thing, what you expect. So what will be the probability of the triple? And so it's the probability of seeing the first part of the history times probability of choosing the action. So which is controlled by the policy pi. So we have here we multiply by policy AT, and then we have history before. Oh, sorry, I was using N as index. And then after knowing the action, we know what is the reply of the environment. So it will be new of observation and reward and given history and action tag. And so by new is semi-measure. Yeah, because we multiply by two conditional probabilities. So if we sum over all triples, we get one. And so remember what is and so we have that sum of by nu of H tilde A and O and R and over A and R and is equal to by nu of H. So this is consequence. Okay, and now we have huge number of definitions. We finished finally. And so we arrived at our semi-measure. And now let us say what is value of policy. And so value of policy against environment. So it will be the logical thing. It will be obtained by sum of rewards. And so we want to I forgot to tell, but it was clear. We want to maximize rewards. And so another example is agent runs around in some computer game or some environment, picks up food, for example, and then the food grows back. But if you take too much fruit or too much fish, the fish doesn't come back. And so, okay, so there are many things we can discuss. So, okay, now let us do some example because it's already many definitions. Okay, so what happens in reinforcement learning is that there is exploration and exploitation trade-off. So agent runs around and agent can like randomly search very far in certain direction to find the great source of rewards. But while doing so, it is saying no to certain smaller rewards in the neighborhood. So it happens, for example, student also faces this dilemma, like you can earn money by working in the shop, filling the shelves, but if you learn special skill, then you can have much bigger reward over a long time. So yeah, so so we can think about like a small environment. So I will now draw the possible actions as a graph. And so there is like exploration trade-off. For example, when we go here, we get reward 1/2. But if we go here, we get reward 0. But later we get reward 2/3. And here we get nothing. And so we can continue such a scheme. So here we get reward 3/4. Here we get reward 0. And we can continue like this. So we have reward 4/5, and so on, and so on. So when we optimize the reward, you understand what will happen. And so the maximal reward, what is the optimal strategy in this infinite game? And so our game will be infinite mostly. When I say the game terminates, it means all future rewards go to 0. So here in this game, once we go up, we can never go down anymore. So the ladder continues like this. And that means that if we maximize the reward, so if we just want an agent and we ask them, give the path with maximal reward. And so when you are in this place, maximal reward is not to go here because there is a larger reward if you go there. So agent will at each step understand this and go down forever and never get something. So therefore, but it's serious problem. It is this is a type of exploitation exploration problem. So So if you artificially tell the agent you will die at this moment, then it will pick the reward right before it dies, and the problem is solved. And so the solution for such types of dilemma is to have exploration time discount function of reward. So so there will be coefficients. So for each time there is a coefficient gamma t, and the idea is that the sum of coefficients is bounded. So sum over t is bounded, and then we will optimize the reward gamma t RT. So we will play the game. The game gives us infinite history, and then the value of given history will be this reward. But what happens when we already n moves in the game? Then we will rescale the reward so that we get something equal to 1. So if we are in the end step of the game, we will start for t equal to n, so optimize the reward. And here gamma n is the normalization factor, and it's a logical thing. It is t equals n to infinity of gamma t. So we will optimize this reward ratio. So this is normalized discounted reward. Okay. So after we understand this, we can. So and then in the seminars we will play a little bit with what happens in the discount. But by the way, if somebody already learned a little bit about reinforcement learning, do you know what is the most popular reward in algorithms? The discount gamma, I mean, the most popular. It is exponential reward. So gamma t is equal to some constant gamma tilde to the power t. So here gamma is 0.9999 or something. It's most popular, but there is 2 pages of blah, blah, blah in the book to say that you should use gamma equal to t to the power minus p, where p is some constant bigger than 1. So, and there's an argument like humans, usually a child thinks like a few years ahead, and then a young adult thinks like 10 years ahead, and old guy of 40 thinks about the time he retires. So it's like proportional to humans also discount, but it seems like proportional to the age they already are. So it is argument from the book. So okay, it might be even true in my experience, but different people have different factor in this role. Okay. Yeah. So now we know how to get probabilities over histories. We know how to calculate reward of a history. So we can calculate, define the value of a protocol against a fixed environment.
Maybe we can repeat the definitions.
Yeah, it's a lot of definitions. Good idea. So if we understand them, the rest of the lecture is easier. So it's very good idea to repeat until it's completely logical and natural. So we have finite sets of rewards, A, O, and R. And so when we speak about computable things in the very end of the lecture, we need to additionally assume that R is rational, or at least computable real number. So we can get any number of digits from R. But okay, for now, we just make sure. So we assume finite. Well, actually, we don't need to restrict. Only when we think about computability, it needs to be finite. But let's keep things simple and keep everything finite. It's more intuitive like this. So then we have probability vectors. So this notion, clearly we need to use it. So we need to have probabilistic strategies. Why do we need it? Well, if we have unlimited time, it's okay to use non-probabilistic strategies. if we are guaranteed to be more clever than the environment, we can brute force the environment. Deterministic strategies are okay. So then you can prove, so we will write down some expected reward and you can prove that it's optimized by deterministic one. But in practice, it will never be used. So in practice, for example, there is how is it called? So there is Q-learning against Markov environments. And so yeah, what I want to say is that as soon as we need expected values, we have to do exponential searches, and then people estimate as expected values using randomized strategy. So that they will have and algorithms will be based on randomized possible moves or randomized explorations of the neighborhood because it's too big. So it's very natural in applications to have random path. Okay, but I distracted. I should just repeat the definition. So mu is environment, which is probabilistic, which is also natural. Then we have pi nu is the semi-measure by multiplying conditional measures. So here we get a measure where the alphabet are elements from here: triples, action, observation, reward. And the definition is the natural one. And so it's inductive. So after we want to extend the probability of the history, we multiply by probability of action and probability of observation and reward. Okay. And here I wrote down the proof that this is indeed a measure. But okay, let's make some space and remove it.
It is same measure or it's the measure.
So it will be measure for most of the lecture, but it's very dangerous remark because in the book they create a mess where they artificially keep using measures, and so it's I will be forced in the notes. I will look carefully when I write it in the notes to generalize it to semi-measure. But for now, let's think that this is measure, not to worry about it. And for exam, I will not ask about semi-measure. Let's keep measure. And I think that maybe it's the right thing to do. There is a way to have semi-measure. So a Solomonov measure that is indeed almost a measure. So we will only violate it on the empty string. So maybe it makes sense what's happening in the book. But then I need to check on all the main applications, and I didn't study it yet. So that's why. I expect we will keep this inequality. Just I will relax this thing here. Okay, but yeah. Okay. So. And this is clear, right? So when we sum over OR, then this becomes 1. This conditional measure, when we sum over A, this becomes measure 1, and then this remains. Okay, so that is. Oh, it says semi-measure. Yeah, sorry, measure.
Yeah,
oh, yeah.
That's why I asked.
Yeah. And I was saying measure. Yeah.
I just thought, oh. It's the definition of measure.
Yeah. Sorry.
Thank you.
Yeah. Okay. And then we should remember about discounting function. And so we will have a sequence, gamma 1, gamma 2, and so on. Discounting sequence. And what we use here is they are all non-negative. And sum of gamma t is bounded. So, but maybe we can have a look to the seminar if there is a nice exercise. So second one I need to draw. So let's just to get used to the definition, calculate a few protocols, deterministic protocols against deterministic environment, and let's calculate the reward. And so let's do exercise that's very similar to what we have here. So let us use gamma t equal to 2 to the power minus t, which is very strong discounting, so very short-sighted. And let us consider an environment where we go like this. So we get 0, 1 reward, but after 2 steps, we can select 2, and so on. And so let us then go like something like this. And so on. So after 1 step, we can pick 1. After 2 steps, we can step 2, and so on. And so the question is, if we optimize this counted reward, which road will we take? And so this goes on and infinitely often. So I have small board today. And then here we can do. So what will be the best discounted reward? So if we want to optimize this thing, should we go inside the first one? Or maybe even let's write the general formula. So alpha to the power t. And so what is the best thing to do when we have this discount? So then we need to write a little formula. So imagine that we go up in the k after the k step here. Here we have some step k. So then after 1, we get 1. After 2, we get 2. So what will be the reward when we go up here? So we get 0, 0, 0 all the time. And then let's say 3 point. Yeah. So
what is n in formula?
This is reward after we already played n steps of the game. So
okay.
Yeah. It is. So this is not. Sorry, this is something technical. We don't need. We don't need it yet. So what's happened? So this reward function is very special. We should think about this. Our policy remains the same after we continue with exponential weights because scaling keeps. Sorry, this is always the case. No, I'm mistaken. So it's all, there's nothing special about it. So we will look at expected reward after a certain number of moves. So there is a second. Okay, but let's forget about this. I will rewrite it later, this formula. So let's first now look. We are in the beginning of the game. So here is the start. And the question is, which node will we choose to go up? According to our reward function. So where we start from t equals to 1 to plus infinity. Gamma t r. So then we should just write this down. Yeah.
If we turn left after k steps, we get k, and that's the sum of alpha power t.
Yeah,
from t k to k.
Yeah,
K plus 1 to k.
1, 2. Let's give some name, 1 and 2, and so on. Then we are in node k. When we go up in node k, we have k plus
from k plus 1 to k.
Yeah, let's take minus 1 here to make our life easy. Otherwise, I have to write plus 1 everywhere. So yeah, so then we have alpha k. It will be so when we go here, And we start with alpha. Here we get alpha. No, I don't think whether my idea is making my life easier.
From k to k minus 1.
Yeah. So when we have 1, we will have alpha to the power k. So, and then we have alpha to the power something like 2k. The last step. And so when we go up in k equals 1, I don't know. So I do that, and then we get 2. Sorry, the -1 doesn't help. Sorry for the mess.
Oh, okay.
Yeah. No, but sorry, it doesn't matter much. So yeah, okay. So this is a reward that we get, and so we can calculate it. Oh yeah, you're right. It does make things easier if I put -1. Okay. Yeah, but the scaling doesn't matter to choose the place where we go up. So we have alpha t plus 1 times, and here we have 1 minus alpha to the power k, 1 minus alpha, something like that. So we have to look to the next power. And so for which k is this maximized? So we have to check for which beta 1 minus beta is maximal. And this will be for beta equal to 1/2. It will be roughly maximal. It's parabola. So we want to be as close to 1/2 as possible to get the maximal value. So if alpha is 3/4, for example, then, or let's say alpha is 0.99, then we will have b, it's around 100 steps, we will go up. So but this makes sense. Like so one way to interpret geometric discounting is to think that you die with probability 1 minus gamma tilde. Or 1 minus alpha here. And so that means if you have about 1 over 1 minus alpha steps, you are half dead already. So it's time to go up. Okay, so this is a little. So we already did one exercise from seminar. And now let's go to value function. So we already calculated value function for deterministic case. So now let us define it. It's very easy. It's just expected value of our reward sum. So, the value of a protocol against environment is just expected value when we generate infinite history from by first by nu or RT, so sum over T, RT, gamma T. And so here I use certain notation. So when there is, so AT, OT, RT. So when we have an H, infinite sequence H, we just denote this triple to be the T triple inside this H. So very natural thing. I just, whenever H is fixed, I will use these names to identify elements of the T tuple. And so now this is properly defined. So value of certain protocol. Okay. So now we also interested in value of protocol after a certain number of moves, after we have certain initial history. So our definition of self-optimizing will have an additional argument. So I need to make a bit more lovely, just to be clever. So we want a value protocol view that depends on a certain initial part of the history. And so here we will use conditional probability. So it means that we already have observed n. So we start summing from t equals n to plus infinity. But it's not right. I forgot the value function is always normalized. So previous definition, I also forgot normalization. Normalization will be important when we define limits of certain things. So we will have here 1 divided by gamma of n. So there will be a special letter for the sum. And this will be the value after we have HT and policy factor. Okay, so what is this conditional expectation? It's natural thing. So you generate random h according to semi-measure, and you throw away all the h that start with different segments. If it's difficult, I can write the correct definition. So we can look at conditional measure here. So let's write it. So let us look to 1 over gamma n expected value, where we generate some history according to conditional measure and from h smaller than n. Then we look to reward from G. Oh, yeah, now it's getting a bit messy because if we have another letter, we can, let's call it R tilde t gamma t plus n. We have some. So here I use R tilde to say that I take the reward from G, and now I generate a fresh list of a fresh history, but according to conditional measure. So that's like how you can write it formally. Conditional measure is the usual thing, like we define it. So we just, so this is equal to. So for every string, so P nu z given each n is equal to mu of so the thing we have been using for some time already. So okay, so this is a lot of definition, but probably maybe this was already clear. So let's continue. So we know what is value. So now we can define the best value and its logical definition, right? You can guess it. So we will take supremum over all possible values to define optimal value. So what is V star of nu? So the best policy, the best value we can get for environment. So it is equal to supremum over all policies by, this is uncountably many, so just all measures we can take. There is a very big set, so we can think like, is this thing even computable? even if R is finite set of computable numbers, O and A are finite, and the measure mu is computable. So then can we compute this for given history? And the answer is yes. But let me write it down. So it is phi of mu of H after post. Okay, and I was using n, so let's try to be consistent. Like that. Okay, so now there is a nice question. Is this thing here computable? Oh, wait, there is something in the chat. Yeah, it's better if you speak because, okay, I can read the notes. Okay, so even if nu is computable, can we compute this thing? And the answer is, well, so what needs to be computable? We want this function gamma to be computable. So you remember, gamma n is equal to sum t equal n to infinity of gamma t. If this gamma is computable and the little gammas are computable, okay, so that there is funny fact that it can happen that gamma is computable, but the sum is not computable. But okay, don't worry about it. That's why I say that both gammas needs to be computable. Then we can, and nu is computable. Then we can prove that actually here we can only use deterministic pi. So the best reply, okay, first, so when I claim it is computable, what do I mean? So if I give epsilon and h, an initial segment h, then I can give this value within error epsilon. So how do I do it? Because here we have infinite objects, so we cannot guess, we cannot brute force over all infinite objects. So, but why can I do at least some brute force search? It has to do with gammas and rewards being bounded. And so we will pick a t large enough so that gamma t, so I'm given epsilon and h smaller than n, and I need to compute this value within error epsilon. First thing I do, I choose t such that gamma t divided by gamma n is smaller than epsilon over 2. So what's the idea is that I will ignore all sums that go after t. So after this number of moves, I know that all the r's are bounded by 1. And I know that whatever comes from the sum will be smaller than epsilon over 2. I will ignore it. And then I will approximate this value here by brute forcing over the next t star, let's call it t star, by brute forcing over the next t star minus n moves. So then I have, and I do all my computation so that I get each sum of rewards within error epsilon over 2. And so this is computable number. So this is just a remark. So now we know what is V star. And now let's go to definition of self-optimizing.
Yeah, what is the gamma star? It's the sum of some number of coefficients, which we
So gamma
star in that
where
formula
is
below.
T star.
Below
No, T star.
T star.
Yeah, I just say large, or I can call it T epsilon or something.
So it's just the sum
It's
of
a special
some
T.
some portion of our
Yeah.
coefficients.
Yeah. So you just how many terms in the sum we have to take so that our result is guaranteed to be precise within epsilon over T.
So we choose just a finite set of an infinite set of coefficients. So we
we choose finite
choose a
set.
bound.
Yeah. And then say what happens later, we don't care because it doesn't affect the value. Okay. Wait, that reminds me, there is another exercise. So the third exercise of the seminar is about value functions. And so the question is to prove that V is linear in the measure. What does it mean? If we take a mixture of the value of policy against a mixture of environments, then the value is the same in the coefficients of the mixtures. So let me write it. Okay, so big gamma is easy to remember. So it's an exercise of two parts. So let us define some measure rho is equal to so alpha is a constant in 0, 1. So alpha mu plus 1 minus alpha mu. So what can you say about this value function here? And so the claim is that rho is equal to alpha v mu. So for the same policy, plus 1 minus alpha v mu. Right? It's by linearity of expectations. Okay, so it's not obvious. So if somebody can say something. By the way, this is important in our proof that we will have in 10 minutes or something.
Again, what is a new
So
yours?
yeah, mu are environments. Mu and u are environments. Environments. So environment is defined here. And so it gives us probabilities for each pair, history, and action. So now the claim is that if we take a linear combination of environments to get a new environment, so it's clear what this means. And so for each history and action, we look at linear combination of probabilities. And the claim is that when we take in this way linear combination of actions, we get linear combination of values when we use 3 times the same policy. So second part of question is if I replace pi, so I don't know, like for somebody it's too fast, some too slow. Question is when there are stars here, why is it convex or concave? No, it's, yeah, it goes, yeah, it's better. So this is better, so value goes up after con. Okay, but first, most of hardest question, why is it linear? Okay, we just have to understand here we have expectation over measure. So let us think that H is empty. So then we have nice measure. We don't need to worry about conditions. Okay, what do we know about yeah, so let us look back to I deleted. And reward them. So now let us think about each term separately inside the sum. So let's pretend that there is no sum, we fix certain t. So we have to think of what happens, what's the probability of seeing these rewards according to the mixture. So it should be linear. Now I admit I'm myself confused. I thought it was obvious, but it was linear. So let's think about the first ripple. There clearly probabilities are so. Yeah, so it's better to think in terms of trees. Yeah, it's logical, but I cannot explain it. So this is very dangerous. If I think it's logical, it means I don't understand it. But so yeah, so what how I view it is I with probability alpha I pick an environment, and then with other probabilities I select this sequence. So I should view it as a chain of events. And then if you're just interested in one event, then maybe sum everything. Uh, but somehow sorry, we just have to prove it by induction. So what do we have? So what do we need to prove? That the rho of H tilde A n sigma n R n is equal to alpha phi mu of H tilde. Oh, sorry. Yeah, H tilde. Nine and plus 1 minus alpha times by mu of H tilde, and then phi times mu. That sort doesn't make sense. No. No, that's not what we need. That's what we need. Very good exercise. That's what we need. Yeah, so this is what we have. This is by definition. Good. Okay, I actually this is something very dangerous going. Okay, let's see that we cannot do. This is very good. So I did something pretty bad. So it's bad idea to define environments like this. So but the problem is with my definition. So actually, I did give you a bad exercise. So no, could we meet this problem now? Okay. I need to define in another way what I mean with the mixture of environments, because this isn't working. So what I need to do is assign not conditional probabilities, but probabilities to so there will be a special type of solution. By the way, in the book there is also a mess, but actually I didn't react well on it. So what will happen? Let me check what's happening in the book. Sorry, I not using a good definition of. So there is a problem with my definition of environment. I'm really sorry. Let me. Okay, so environment is defined as a mapping of actions. So the definition in the book is pretty annoying. I believe that I could be smart and have intuitive definition, but then I understood that I cannot take linear combinations anymore. So yeah, it's bad, but okay. So we have a mapping from A to semi-measure, to measures. So they have the notion of chronological measure, but it's also very, it's closely related, but the requirement, so there is extra requirement on this. And it is that hold on, hold on. Okay, I will just, so that they don't give formal definition. I can write what they write, but it's also not nice. Okay, so they start, so they start with what I originally wrote. Probability over for all times required. But then they immediately change the definition, and then they say, we say that the new of so that there is an extra letter. This is very annoying. They say that this A D is equal to the product of new ET given HE8. So where ET is a pair of observation reward. Okay. Yeah, it's school result. It's from, so in the new book, everything has changed. I didn't see it in the new. So this is, of course, a worst case trouble. I mean, teacher under time pressure, all new research results. But I really wanted to teach this because I thought it's cool to present a reinforcement agent that can learn every environment, even though the algorithm is not so useful or practical. But now, yeah, there is brutal punishment. I cannot clearly explain things. So they say that from definition, they start from such a mapping, but then say the actual object is a function that's defined in such a way. So if you give it a list of pairs, observation reward, so here is observation, so E of T is equal to the pair observation T reward T. So if we give it a list of observation reward T, then it's assigned a probability according to this conditional measure. And then he says, when we add two, and when we take a mixture of two environments, we take the mixture of this object. And this is very important in the proof I hope to explain, but of course I should not make another such mistake. Otherwise, our goal will fail. Okay, and now let us, after we get correct definition of taking linear combinations, that's all. So here the product goes for T equal to 1 from 1 to N. So note that, so again, when we take linear combination of environments, we take linear combinations of products. And now this exercise, which was wrong with previous definition, becomes trivial. Why it becomes trivial? Because let us look to our definition. Okay, so so now let us look to our definitions that we have. And so when we expand this thing here, what do we recognize? So if we expand this recursively, we have a product of all our actions times products of all our conditional measures. But then this is very good news, because here in our expectation, so in our definition here, we also take mu is now associated to product of conditional measures. And so we need to think, when we think about linear combinations, we must think about this measure mu, the product of conditional measures. So here we have products of conditional measures. And when we multiply by the same probabilities on actions, then the semi-measure inherits the linear combination. So the convex combination, actually. Right? And so now this is trivially true. So when he writes mu, it is product of conditional measures. So when we write conditional combination, then we take a linear combination of the products of conditional measures. So basically I should write, let's write the arguments in full. So what we have here is rho of En given An is equal to alpha times mu En An plus 1 minus alpha mu En given, 1 minus alpha mu of, with the two lines here, mu of the same En given actions of okay, and now this so this is wrong. Now, fortunately, so now we have pi rho equal to alpha times pi mu plus 1 minus alpha pi mu. So it's okay now. Okay, so let's look to a definition here. So when we expand this, we have a huge number of factors, right? Let's group them. The factors that belong to pi and the factors that belong to nu. Factors that belong to nu, they group together with this double bar notation, as this function with double bar notation. And so now let us understand, when we substitute rho here, we have the same factors for the pi's. All our factors for pi's are together. But when we have rho here, we get a rho with the double bar. But the rho with the double bar, we can expand using the convex combination, because the main object is this thing with all, with the double bar here. And I forgot the double bar here. So now it's trivial, okay? So this is almost by definition. And so second part of exercise is what happens when I replace pi by star. So we look to the best policy that optimizes the value. So yes. So the claim is that in this case, we have inequality here. It means that our function is convex in the environment. They're convex. I make the happy face. Yeah. Okay. So, and why do you think this is true? Well, let's look to policy that optimizes this one. So here we have, so this is equal to v rho of some pi. So some optimal policy, so the best policy here. If we apply this policy here and here, we get equality. It's our previous result. So if we take best policy for mu, it can only increase, and same for mu. So we've proven that it's convex, but we don't need this anywhere, it's just exercise. And it's very good that this exercise exists, otherwise there was a huge disaster in the next school. Okay, so now we have some experience with value function. And it's time to say our main result. We need one more definition. So convergence with probability 1 is our definition. So we will say that, so let me make some space. So we will draw histories according to our semi-measure here. And we want to say that two functions converge to each other with probability 1. So we want to say that value function of our special semi-measure converges to value function, the best value function. So that's why we need this convergence. So we will say that, so f, we will have a function of histories and converges to some other function g of histories with probability. So with mu pi, let me write it on the bar. With pi mu probability 1 when n goes to infinity. So what does it mean, converge with probability 1? So it means that, and I need a little bit more space, it means that for every epsilon, bigger than 0, we have that limit that these functions differ by more than epsilon goes to 0, the limit probability. So we have minus. So f of hn minus g of hn bigger than epsilon is equal to 0. So the limit for n to 12 infinity and the probability for h from pi mu or distribution. Well, can be any semi-measure, of course, but we will apply it with this thing. Okay, and now we will say that policy is self-optimized. So we have a protocol that is self-optimizing in a set of environments. So one more definition, a set of environments so the set of mu's here. And then we say that pi is self-optimizing and we need certain so we will use convergence. Okay, let me write it first in a way that doesn't make sense. So if for every environment mu in n, so the value of the policy converges to V star. And so the two V's converge to each other for this policy. So we have E pi H n converges to V star of H n. And so here is n goes to infinity. So for n going to infinity, this converges to each other. The question is, how should we select the histories? Because imagine that you're playing a game and then you generate stupid histories where you suicide. Then every policy is self-optimizing. If you start from such, if you compare to such a distribution where this happens. So you can play optimal if you trigger trivial environments. And so the definition is that it's self-optimizing compared to a certain historic, to historic policy. So pi is self-optimizing relative to historic policy. Okay, historic policy pi tilde. So when we take, so we have with pi tilde mu probability 1. Okay, it's barely readable. I should rewrite it somewhere. So, okay, I will remove. Let me copy it. So I will remove this part here. So not so much space. So pi is self-optimizing. For n relative to historic policy pi tilde. So if for every mu in the set of models, we have that V pi against the value of pi mu of small n converges to V star of mu, starting from history n. So we take long histories and we sample it from reference policy pi. So we take it. So the idea is that we take a clever policy pi, and in the result we will have quantifier over pi. So we will have such a result for all. And so here we say that n should go to plus infinity, and with pi tilde probability 1. Pi tilde mu probability 1. So this is definition of self-optimizing. Okay, this is our main theorem, main definition. And now let's state the theorem. And it's time for break here. Okay. So again, I need some space. And I can remove this because the theorem is quite small. So the theorem says if there exists some self-optimizing, okay, first, oh, sorry, we need one more definition. We didn't define our special strategy yet. Okay, so what's our plan to define special strategy? So we will take a countable M and then take just a linear combination of all environments of N, but we take a combination of these chronological measures. So, and this is called in the book, it's called Xi. Try another marker. So we define Xi. And so with this double bar notation, E double bar, A double bar N is equal to sum over all mu in the model. And then we assume we have some weights mu. That's why I say M should be countable. We can put all the measures in a list and then we assign a weight to them. And then we take the chronological measure E of N given P with 2 bars. Okay. So the claim is that the policy that optimizes Xi. So let us, so we need a notation that pi of Xi. So know that this is defined as a supremum. Suppose that supremum is a maximum, then we have a policy pi. Then we can fix a policy for every environment, we can fix a policy pi Xi. And this policy is the one that achieves the supremum. And this policy that's optimal against this mixture of all the measures will be self-optimizing, provided there exists at least one self-optimizing policy. So that's the theorem. So now you know all the definitions. So Xi achieves V star of Xi. And now I need the theorem somewhere. So let's forget about the discounting. Theorem. If there exists self-optimizing policy pi relative to historic policy pi tilde, and for the set of models M, then the pi that optimizes the mixture is also self-optimizing. And then relative to pi tilde. And then the model M, of course. So that's our result. And so now it's time to have break. I still need to explain the proof. But yeah, it will take half an hour, but we also did 2 exercises from seminar. So yeah, maybe even less than half an hour because we already very well understand this crucial point. Okay, so let's have a break and then I will continue like 5 minutes after 8, or if you say we want
Okay.
to yeah, let's take, you can also say let's 50 minutes work hard and then stop earlier. But maybe, yeah, it's a very long lecture. Yeah, all these definitions and no proofs. It's hard to focus without. But okay, we had some exercises.
Yeah, but just when you when I think for a really long time, I can't focus
Yeah.
more, and I
For
want to
me,
have a
it's
break.
like oh wait, let's first stop the recording and then